So up next, we have Nova folding with MACI Circuits by Chao at PSE.
Thank you. Hi, today I will talk about the Nova MACI. So basically, we apply the Nova folding scheme on the MACI circuits. So my talk consists of 3 parts. The first, I will give a brief introduction to MACI and Nova. And the second part is about the engineering implementation. And the last is about the future work. So MACI stands for the Minimum Anti-Collision Infrastructure, which originally proposed by Vitalik. And this is an anonymous on-chain voting system. So the major issue the MACI wants to solve is the off-chain bribery issue. So basically, Alex can buy the Bob's private key and voting represent the votes for the. So basically, Alex can bribe Bob and buy his voting key to vote for her. So this is a major issue MACI wants to solve. And the underlying technical part is about using the Circon, and the backend is GRUS16. So this is our current implementation. So there are various applications, such as anonymous voting, as well as anonymous, like a quadratic funding, so like a clear dot fund and QFI are 2 such projects. And the code base is under the PSE repo. So Nova stands for the recursive zero knowledge argument from the folding scheme. So Nova is one kind of the IVC, and IVC stands for the incremental verifiable computation. So the traditional or the before the Nova, the IVC usually involves to verify the proof for each of the step circuit. And after the Nova, instead of verify the proof, we can just extract the accumulator, or what in Nova called the R1 CES instance from the IVC circuit and fold it into the running instance. So you can assume this is also kind of the accumulator from the traditional language of the IVC, but without verify the proof of each step. And there are basically 2 components in the IVC circuit. So one component is we have to write a circuit to prove the step circuit function is correctly executed. So the input, for example, at the step I is Zi, and we have write a circuit. So F is the step circuit function. Output will be Zi plus 1. So this is one part of the IVC circuit. And the other part, we have to correctly folding the little UI and capital UI. So here the little UI is basically extracted from the IVC circuit as accumulator. And the capital UI is kind of running accumulator. So basically contains the information from all of the previous steps we have running for the IVC circuit. And the recursion overhead for the IVC circuit is kind of minimal. It's only dominated by the 2 scalar multiplication. And the Nova code is also show up here. Nova Scotia is a library written by Nalin. This is used to transform the Circon circuits into the Nova step circuits. So we can using the Nova Scotia together with Nova to just folding our MACI circuit. So that is all the tooling box we needed. So the second part, I will talk about the engineering detail about the implementation. So here is the basic workflow. We're starting from the MACI contract and the MACI circuit. So from the MACI contract, we're basically using the MACI CLI to extract the necessary states as the circuit inputs. And also MACI CLI will generate the R1 CS file needed by the Nova. So with this output, the Nova will call the Nova Scotia to the R1 CS file to get the public parameter, which is depending on the size of R1CS, and also create the IVC circuit from the information of the R1CS. And also, we can generate the witness from the circuit input and the R1CS file. So with all of this output from the Nova Scotia, we can directly call the Nova library. So basically, Nova library will take the output from the Nova Scotia and generate a recursive snack for each step. So suppose we have n step, we'll just apply this n times to get a final recursive snack or the compressed recursive snark. So as the last step, we can just call the verifier. So currently, we have the off-chain verifier writing by the Novas library. So writing in Rust, we can verify it. So after the verification passed, it means all of the previous n steps is correctly. So this is basically the workflow. And the next, I'll talk about the cycles of elliptic curves. So basically, in Nova, we're using the cycles of elliptic curves. The reason is that the dominating operation is the scalar multiplication, and the elliptic curves contains two fields. So suppose here, the definition of the elliptic curves is y squared equal x cubed plus ax plus b in the Weierstrass form, and the xy is the coordinate, and they belong to the base field. And whenever we have the scalar multiplication, lambda times the point on the curve, this is basically the lambda naturally located on the scalar field. And for the pairing-friendly curve, we cannot find such field that fp equal fr. So the best we can find is like cycles of curves. So basically, we can find two curves, E1 and E2, and they satisfy the same equation. So basically, A and B is exactly the same for this E1 and E2. However, the base field of one is the scalar field of the other. So when we write a constraint system, the constraint system is naturally using the scalar field. So whenever we want to do some operation on the base field, for example, for the scalar multiplication, this involves a lot of operation on the coordinate, which is the base field. So one way is we can using a non-natural field, using the scalar field to emulate the base field. To do this, we have to do the big integer operation. So this is the cost is higher than using the natural field. So one idea is without this kind of operation, we can using the constraint system of the dual curve, because the dual curve's scalar field is equal to the base field of the current curve. So basically, we can have two running system, constraint system, and whenever we want to do the base field operation, we can use the dual curve constraint system to verify that. So basically, here, the most heavy operation, what I mentioned, is the scalar multiplication for the elliptic curve point. And the example is, there are, for example, the Pallas Vista curves. This is one type of dual curve, and is used in the Nova implementation. And there's another curve called the BN256 curve. So this is what we used in the MACI as well as on Ethereum Solidity. So basically, and luckily, we also have the curves for the BN256 curve. So basically, the cycle is BN256 and grouping curves. They also form a dual curve. And the next slide will be the engineering work on this implementation. I just listed the major part we needed to do. So from the MACI part, the first thing is we have to change our circuit interface, follow the standard defined by the Nova. So basically, you have an input of the step circuit and output of a step circuit. And the input and output format and the dimension should be the same. So basically, ZI and ZI plus 1 look similar format. And the ZI will be the information, for example, the hash of the state and some auxiliary variable, such that the index of each batch. So here the state means the state is defined as the hash of the root of state tree and the root of the battle tree. So basically contain, whenever we process the voting message, so the voting message is extracted from a smart contract as anonymously. And whenever we process each message, we actually updated the states of the state tree and the battle tree. So whenever we apply this step function once, here the step circuit is a MACI circuit, we updated the state. So with this modification and some other modifications, such as like an on-chain solidity verifier for the growth 16 and like a CLI to generate circuit inputs, with this setup, the MACI part is done. And for the Halo, so basically, as I just mentioned, we have to support the BN, so basically the BN256 and grouping curves using the MACI. Using the Nova. But originally, the code only supports the Pallas and Pasta curves. So we have to add the support for new type of curve cycles. And luckily, in the PSC repo Halo 2 curves, we already have such curve support, the BN256 and grouping. However, one of the algorithm missing is the hash to curve algorithm. This is used to generate the public parameter or the commitment key for the Nova. So we have to add this support. And in the beginning, I just write a simple try and increment algorithm to unblock my development. And later, I discussed with Han from the PSC team, and he added a new SVDW algorithm into this repo. So later, I will replace my current simple algorithm with Han's implementation. So with all of this Halo 2 curve support added, we can add the support in the Nova repo to support the BN256 and the ground peaking curves. So with this, we have to modify several, basically Nova defines several traits required by when you add into elliptic curves. For example, the group trait, which contains the hash to curve algorithm. So with all of this preparation, we can do our benchmark. So here is the code base for all of the dependency we have. And for the benchmark, I have tested the state tree depth for the 6. So basically, all of the tree here is a quinary tree. It means, for example, the state tree depth is 6. So we have a total of 5 to the power of 6 maximum users. And the message tree depth is 8. It means we have the 5 to the 8 maximum messages. So with all of this setup, the R1CS file is about 500 megabyte, and the Z key is 1 gigabyte. The PTAL file and the public parameter for the Nova is similar size, like 4 gigabyte. So this gives you some rough idea of the size of the circuit. And I have tested the various combination of the user and the vote per users. So basically, this bench result is kind of linear with respect to the total voting message. So in this case, we have like 100 user and 10 votes per user. So which is 1,000 votes. According to this, like a message batch tree depth is 2. So basically, you have 5 to the 5 square, 25 per message per batch. So you have the 1,000 divided by 25, which is 40 batches. And you can assuming from the MACI perspective, we treated batch by batch. So each batch is kind of one step of our circuit. And here is the benchmark. The time cost is in the unit of seconds. So the generate circuit input is common for both MACI and Nova MACI. This is written in the MACI using JavaScript, is unoptimized, and the most time-consuming part is about 460 seconds. And for the creation proof for MACI part, is everything for the create proof except the generate circuit inputs part. So this is about like 170 seconds. And because as we just mentioned, when we do the Nova folding, we don't need to using the proofs. So there is no such step to create a proof. And we only need to do the folding. And so Nova MACI for the folding part, the total time is about 38 seconds. So it's using Rust. So as you can see, for this part, it's faster than the MACI. However, the current dominating time is still in the generate circuit inputs. So I would say in total time is kind of slightly better from the prover side. However, because we are using IVC, it means in this test case, we have 14 batches. So in the original MACI, we have to verify on the Solidity verifier 14 times. However, with this setup, we only verify one time for the last step. So basically, you greatly reduce the verifier on-chain gas cost with this approach. So that's a benchmark result. And the future work is, so the first thing we have to add is on-chain Solidity verifier. So currently, I'm only using the off-chain verifier already using right in the Nova library. So we have to export the verifier to the Solidity so we can implement a smart contract verifier. And because the Nova using the Spartan verifier, so this is something we plan to do. And the next is add the support for the other MACI circuits. So currently, we only do the circuit for the process message for all of the users' voting message. The next, we'll do the tally votes and the subsidy calculation. So this is the 2 other features in MACI. So that is all the future work. And thank you. And here's the reference.
Hello. So my question was, did you explore the idea of basically verifying the Nova proof in another snark prover such that then you can verify this proof efficiently on chain, like verifying the Nova proof in a gross 16 prover. So you basically reduce the size of the Nova proof and you eventually verify it efficiently in on-chain. So you don't need to write the Nova verifier in Solidity.
Yeah, I think, so you mean instead of using Spartan verifier, we verify this using the like gross 16, right? Yeah, I think this is another option. So for the on-chain verifier part, so so in these slides, so here the recursive snark is something without the ZK and without any compression. So we can using alien backend, for example, in the Nova's original paper, they just using Spartan, but we can also using like gross 16 as to compress the recursive snark. So in this case, we can write in, let's say, gross 16 verify on chain. Yeah, so we can just decide which one to choose, yes.
Okay, do you know if this tooling are already existing?
I don't know if there are already existing one. If it's existing one, we can just use it, yeah. Otherwise, we will just implement it ourselves.
Yeah, cool, thank you.
Just wanted to say quickly on that, it does exist. It's called Testudo.
The gross 16?
It combines Spartan with gross 16.
Oh, okay, cool. So I think I will search for that.
Any other questions?